Now, special relativity has been something that it's been engraved in our minds for a long time now. And we always have the implicit assumption that all of velocity is relative to each other. And I'm going to challenge that fact based on what I've just kind of figured out. Now, I made another video called True Solutions to Twin Paradox. And because of that video, I ended up making a video regarding the twin ruler paradox. And because of that video, I kind of gave me a eureka about something that everybody, including Einstein, overlooked. Okay, so again, not clickbait, just watch it. Let's look at this scenario here. Okay, so let's think about this for a second. Imagine that you were teleported to a dimension where there are no planets or stars. All you are is you're on a spaceship that's 1 light year in length. That's all there is. And your friend Charlie and David are on another spaceship that's also 1 light year in length. Oh, okay. And you two the two spaceships are almost touching each other. They're kind of in line here. But all of a sudden, you see that spaceship starts moving at 0.6 c. Or alternatively, is it your spaceship that's moving towards them at 0.6 c? You don't know that. There are no planets, there are no stars, there's no way to determine who is moving and who's not. So your spaceship keeps moving, or their spaceship keeps moving. Again, both spaceships are 1 light years in length. Okay, now, is there a way to determine absolute velocity in this case? And what we know about classic special relativity is that there is no way of knowing that. At least that's how we've thought about it for the last 100 years. In fact, this has affected a lot of our perspectives. So, for example, there's a thought experiment in which is that, what if the entire solar system or the entire galaxy, the Milky Way, is moving super fast to a certain direction? Would we have no way of knowing that? Again, if all velocity is relative, then no, we don't. And we're in a universe, or a dimension in this case, that has no planets or stars at all, and no way of determining if you're stationary. So, in this regard, then neither side can know that who's moving and who's not, and both can say the other one is moving. I mean, that's the whole basis of the twin paradox. And in this case, there is absolutely no way of determining who's moving. Or is there? Now, what if I'm telling you that all those assumptions were incorrect, and that there is indeed a way of determining who is moving and who is not? Think about length contraction. Okay, now, in our example, I said that the two ships are stationary, and then one starts to move. Again, we don't know which one's moving. Now, the other example would be, what if the other ship simply moves towards you? There's never a point where they're both stationary. I'll talk about that later as well. And I will pick the first example in which there's two stationary ships at first, because it's actually easier to figure out. The second example is a little bit harder in the math, so it's more complicated. The second thing is, for this example, we're going to assume instantaneous communication that we can make to the other ones to, talk to them and so we can figure out who's moving, who's not. Now, understand that technically, any kind of signal will be limited to the speed of light. And indeed, we could actually do those calculations without sort of instantaneous signal. We could use the speed of light through our calculations, but all it is, it just makes the math more complicated, and I figure that's just harder for people to grasp. I will also talk about that. But for the start, we'll do the simplest thing possible. We have two stationary ships. One starts to move. Let's figure out which ship is moving, or can you even do that? And I'm going to tell you, yes, you can, and that what we know about special relativity, we made. Again, I'm not saying there's definitely some mistakes on special relativity that experts and scientists have overlooked, and I'm here to explain that. Now, when I first imagined the video, it was actually a little different, and I realized that making these ships 1 light years long each actually makes things more complicated, because, again, this is the way light travels. Just pretend that they're like 1 kilometer each or something. Don't worry about the light year unit, just pretend that it doesn't exist, and when I say light years, just pretend that they're not that long, because it does make things more complicated than it needs to be. Okay, so let's figure out what exactly we'll be seeing before moving to set up that initial scenario. So first of all, is that, again, there's a 2 light year distance added together, right? Because each of these is 1 light year apiece. And when one object starts moving, again, we don't know who's moving, not yet. Both sides will see the other object as contracting in length. See, the thing is that we're having the assumption that there is total symmetry, that everybody will see the other object as exactly the same. But all we need to do to determine who's moving and who's not is figure out if there is indeed total symmetry, and if there is a broken symmetry, then we can figure out who is the moving object. Okay, so here's how it's going to work. When B thinks C has passed it, B will trigger a signal that will cause everyone to take their snapshots at their moments. And which the 4 snapshots will be A, B, and C, D. So all 4 people will They're snapshots of that moment. Now, here's the thing. Signals are still limited to the speed of light. I understand that. But for the sake of this first example, we're going to say that the signal in question will be instantaneous. I know a lot of people are going to say that's not realistic because obviously, if he's going to use radio to tell A or C or D to kind of record the sound, that needs to be at the speed of light. But we could do that. It just if we do those calculations, it just makes it harder because you need to calculate this time in which you travel. And it's going to make this example way more complicated than it needs to be. Now, I will say this. We don't need an instantaneous signal. We could limit our signal that B can trigger to the speed of light. But that changes how this calculation won't have to be done. And it makes the calculation about 10 times more difficult. It's still doable, but just harder. But for the sake of the example, we'll just say that signal instantaneous. Okay, so you're going to be wondering a very simple thing. Now, why would any of this matter? Wouldn't the four people see the exact same thing? And the answer is no. Okay, see, length contraction is interesting because length contraction, you understand where that object will contract in length. So let's suppose you have an object that's, a certain fixed length, and that object suddenly starts moving. You will see that object contract. But where would the center point of that contraction be? And I made another video about it, and again, we'll just say, keep it simple here. It's very simple. It's going to contract down the center, right? So if this thing, imagine that C and D are totally stationary, they're 1 light year. And as soon as C and D starts moving, they're going to contract down the center of it. So what it means is that there will now be a gap here and a gap here compared to the original shape, right? Because again, it's contracting to the center. The length contraction is based on the center of that object. And may this be a train, a spaceship, or in this case, a flying spaceship. Now, if, on the other hand, for someone on a spaceship or a super fast train, where the entire universe or entire train track is contract in length, where would the center point of that length contraction be? Well, it's very simple. That's going to be on the point of view of the observer. So it will contract on the point of view of that observer. You see that, and this is the first time where symmetry breaks. When we have symmetry breaking, that's when we can determine who is moving and who is not. So let's take a look at the actual calculations here. Okay, so as I've said, everybody does their measurements. So we have 4 observers, A, B, C, and D. They do their own measurements of the snapshots of the system. And when we get this information back together, we can figure out who is moving and who is not. Again, let's take a look at everyone's results first, or everyone's observations first. So when we ask A, AC thinks that they're at t equals 0, so just as C starts to move, again, we're doing instant acceleration here. It's going from 0 to 0.6 C. Again, this is a different dimension, so just work with me here. A says that, look, I saw there was a gap of 0.1 light years between B and C. Okay, then we go to B's perspective. What does B see? Okay, B says, well, actually, I saw the exact same thing. There is a gap of 0.1 light years between B and C. So as soon as C started to move, he was no longer right next to me. Again, the initial system, the C and B are practically touching. But as soon as everything started to move, again, we don't know who's moving yet, B saw a gap and A saw the exact same gap. Okay, so there's no problem here. They definitely have symmetry. They see the same thing. And then we go to C's perspective, and C sees something else entirely. So from what C said is, when t equals 0, when everything started to move, or when something started to move, there was no gap between B and C. No gap at all. And again, we can see the distances, the relative lengths, right? So C thinks that they're 1 light years. C thinks AB are on the 0.8 light year ship. Again, and vice versa for A and B. So C saw there was no gap. Then we go to D's results. What is D's snapshot? D, however, says that actually, when everyone started to move, there was a 0.2 light year overlap between the two ships. So B had already passed C at this point. Notice how there's a discrepancy. B and A and B thinks that they haven't even met yet. There's still a gap between the two. Whereas B says that from D's perspective, B has already passed C. In fact, D and C don't see the same thing, even though they're on the same spaceship. And even though their times should be exactly the same. Should they? I mean, again, if they're moving or they're not moving, they should be undergoing the same time dilation or lack of time dilation. Yet, they see 2 completely different events. And with this, we can figure out who is moving and who is not. Okay, so there's probably 2 questions to this. First of all, how can they possibly see different things? Isn't everybody symmetrical? And 2 is, even if they do different things, how exactly can we figure out who's moving and who is not? Okay, and I'm going to answer both of those same questions with the same answer. And here's the thing. Remember, when we have length contraction, we have a center point of that length contraction, meaning that if the object is moving, we would see its length contraction start at the center point of that object. Inversely, if we're on a moving object, then we would see length contraction to our point of view. Now, when I say our point of view, I explicitly mean our point of view. If we are on a specific point of the ship, let's say we're at the end, or we're in the middle, or we're somewhere here, that will be the center point of the entire length contraction of, well, in this case, the universe. Again, if we're on a really long train, and we're on a super fast long train, and we're at the end of that train, then the length contraction we see from the train tracks would be still centered on our point of view. Inversely, if we're on the front of the train, that center point of that length contraction would be to their point of view. So notice, that's the thing. Because C and D are on different ends of the ship, their interpretation of length contraction is different. A and B, however, see the exact same thing. And that is why we know that C and D are the ones that are moving. So let's figure out what everybody saw, and we just simply work backwards from that. Okay, so what A saw and B saw, they saw the exact same thing. They saw a ship contract in length, and then create a gap of 0.1 light years. Now, why would that be 0.1 light years? Again, the ship itself is 1 light years. If it contracts in length, wouldn't there be a 2 light year gap? Or because, remember, an object's length contraction is through its center. So, let's suppose if we have a moving ship, then that ship will contract to the center point. So, naturally, from the front of that ship, 0.1 light years will contract. And the back of that ship, 0.1 light years would also contract. Therefore, we can determine that C and D are probably moving. Because again, there's a length contraction to the back and the front. Right? That makes sense. But, before we jump to conclusions here, let's look at C and D's perspective. Now, from C's perspective, again, A and B saw the same thing. C and D did not. From C's perspective, there was no gap. Now, how could we get to a point where there is no gap in length contraction between C and B? Well, very simple. Remember, the length contraction is from a center point. So, the only way for there to not be a gap is if C is the center point of that length contraction. And if that's the case, again, that's the only way for it to do, then length contraction, again, the entire universe, or this dimension would contract from C's perspective. So whatever's here is going to contract to the right, and whatever's here is going to contract to the left. Now, obviously, C and D's not going to contract because they're on the same ship, right? So that's always going to be 1 light years. But, therefore, C would see A has come closer to it, but B has stayed the same place. A is now 0.2 light years closer to it, because again, this ship has now contracted in length to 0.8 light years. But B has stayed the same place, because C is the center point of that length contraction, because C is probably the one that's moving. Now, let's look at D's perspective. Now, D saw an overlap. Now, why would D see an overlap? Well, very straightforward. Let's assume D is at the center point of that length contraction. Well, if D is the center point of that length contraction, then everything this way must contract downwards. Now, how much length contraction would there be? Wouldn't there a contraction of only 0.8 light years? Exactly. So, let's suppose that D is moving. Well, then again, this distance was really 2 light years, right? The total distance. Again, as I said, the total distance together was 2 light years, because both ships are 1 light years each. When there's a length contraction, again, if suppose D is moving, then the entire distance of that 2 light years will contract down to 1.6 light years. Because again, 2 light years to 1.6 light years, which is again which is actually 2 times 0.8 light years, because that would make sense when that contracts down. So again, this distance from D to A is now 1.6 light years. And then, therefore, if there's a 1.6 light years difference here, then 0.8 light years, but A and B's ship is 0.8 light years, and naturally, B must have passed C to form the 0.2 light year overlap. So, we take a look at that again. Now, I'm going to put the boundary distances at the bottom to fully kind of explain how this length contraction is working right now from A and B's perspective. A and B are stationary. We know that they're stationary because they saw the same thing. And they saw the length contraction that would make sense, the gap. Again, the total distance is 2 light years, but because C and D have now moved and length contracted, there's now a gap of 0.1 light years each from both ends. So naturally, they saw a gap of 0.1 light years. They did not see a gap of 0.2 light years or any other number. It's exactly 0.1 light years. At the opposite end, there's also a gap of 0.1 light years. Now, let's look at C's perspective. Now, why would C see no gap? Well, here's the thing. There's a movement of again, the entire length contraction of the universe, or the dimension in this case, has contracted down from 2 to 1.6 light years. So, now we know A is the end of that distance. So A is right there. A is still 0.8 light years away from us, and B has not moved at all. Again, length contraction is to the center, and it makes sense for B not to move, because B is already with us. How can B possibly contract any further point? B is already 0 distance away from us. No amount of length contraction is going to change that. A, on the other hand, is 1 light years away from us, and when the AB spaceship contracts, it must move 0.2 light years, because A must contract, because again, their ship has now contracted 0.8 light years, so naturally, A must now be 0.8 light years away from us, since B is already with us. Again, because we are already with B, we're already touching B is a distance of 0, 0 cannot contract in length. So it must be A that's contracting in length, and you can see it right there. And similarly, if you're wondering where that gap is, that gap will show up again. See, now, that this distance of 1.6 light years, there's now a gap between C and D. Now, if there was, let's say, a marker point of something there, then you would actually see this gap. Now, since there isn't a marker point, you wouldn't actually see this gap because, again, there's no reference point of that in this scenario. Now, let's look at D's perspective. D saw an overlap. Why would there be an overlap? Well, again, the entirety of this direction is contracting to D, right? The length contraction is going from left to right. That 2 light years has contracted to 1.6 light years. So, at t equals 0, when everything starts moving, A is now 1.6 light years away from D. Okay? Now, if A is 1.6 light years away from us, and we know that, and again, we saw, from our perspective, the ship A and B are on 0.8 light years, and naturally, you subtract that, there has to be an overlap, 0.2 light year overlap. Because this is 1 light years, this is 0.8, this is 1.6, there's now an overlap of 0.2. So from D's perspective, B has already passed C. So, again, let's just think about that for a second. A and B saw a small gap, half gap, if you will, of 0.1 light years. C saw no gap. Well, D saw an overlap. And that's how you determine who is moving and who's not. So there is indeed a way of determining that velocity. So how we're really doing this is very simple. All you need is, the best way of determining it is that you need 2 observers on whatever ship or planet or object you're in. So let's suppose you want to determine if Earth is moving a certain way to a certain direction. Then you need to have both ends of the Earth, or have a satellite or whatever. They have some distance away, and they measure relative distances and, calculate the relative times with each other. Now, we're not in time dilation, so if we have 2 different observers on Earth, we're not in time dilation with each other. And if we calculate that, we can probably calculate some complicated geometry of figuring out if we're moving relative to another object, of another object's relative moving to us. That's actually really cool. Suppose there's an asteroid moving a certain direction, perpendicular, or certain direction towards or against us. We can use this to potentially calculate if maybe we're the ones that's moving and they're the one that's not moving. Who is the one that's actually moving? But the only caveat to that is that we don't actually know the true length of an object, and we're only talking about objects that are moving at 0.5 light years. So right now we're using telescopes that are naturally balanced of light. So, maybe some physicists using more complicated math can explain to me how this could be carried out. But I'm using examples of 0.6t. We're talking to asteroids that are we're moving as nearly as that fast. But potentially, we could use this as a tool determining relativistic velocity and who is moving and who's not. Okay, so I hope you guys aren't too confused, because I understand this is a lot to take in. Okay, so what we're going to do is, as I promised earlier, we're going to do an example in which case we have 2 ships who are simply moving towards each other, or relatively moving towards each other. We don't know who is moving towards who. So this will be the example here. Again, ignore that. We'll just say that there's 2 ships, and there is relative motion between the 2. And how would you interpret who's moving and who is not? And surprisingly, we can do that. In this case, there's no actual stopping point. So at the beginning, the first example, we have 2 ships that are side by side, and one starts moving. In this case, we'll just say one is moving off screen. So here's what we're going to do. We're going to pretend that we're on C and D's ship right now. And at a certain point, they're going to have a clock, and they'll decide on the exact time in which they're going to take a snapshot and measure distance. And what they're going to do is compare that distance. And that's really all they need to do. And now, that is very, very simple. And I'm going to explain why it's such a simple way of solving the am I moving or am I stationary question. Okay. Now, this picture here is called the true measurements, and it's just here to kind of let you guys know of what exactly is happening, because I figure without this, you guys don't really have a context. So what we're going to have is that the true distance will be that there's a gap of 10 light years between B and C, assuming this would be what it would look like if nobody's moving. Now, remember, C and D has a distance of 1. So the distance between B and D is actually 11. So keep that in mind, right? So C and B is 10, while D and B is 11. There is a gap. There is a gap because there's a distance between C and D, which is 1. This number will come up, and this is the critical reason why we can figure out if we're moving or stationary, and why there is absolute velocity. Okay, so let's look at C's perspective. What exactly would C measure? Now, if C is moving, or if this ship is moving at 0.6 C, then C, of course, time length contraction between itself and B. Remember, the distance here was 10, correct? There's a distance between 10 between B and C. So, when C is in motion, then this entire space gets length contracted, so this length now becomes 8. So C and B has a distance of 8. Okay, now remember, we're going to call the distance between B and C to be the gap distance, as in that is the distance between the two ships in motion. Okay, so that's like the gap distance. Alright, so C interprets a gap distance of 8. So let's look at what D interprets. Okay, so D has a distance, remember, up here, D's distance to B is 11, right? Because it's 10 plus 1, because C and D has a distance of 1 to each other. So naturally, the distance is 11. B and D is 11. So when D is in motion, then that length contract distance of 11 will length contract down to 8.8, right? Because it's a distance of 11 contract down to 8. It's actually the same multiplier as C's distance. Remember, C is distance of 10 times 0.8 becoming 8. D has a distance of 11 times 0.8, which becomes 8.8. Okay. Now, that is not the gap distance, because that's the distance between B and D. So, how do we find the gap distance? So D will see there's a distance between C and B. Well, that's actually not very difficult, is it? Because if D has a distance of 8.8 to B, and C is one distance away from D, then the gap distance that D sees is a 7.8. So from D's perspective, the gap distance between B and C is 7.8, but C interprets that distance as 8. Notice how there is no symmetry. Despite C and D being on the same ship, experiencing the same time dilation, they do not interpret the same gap distance. So what would happen is that once the ship starts moving, when the ship moves to meet the other ship, because D interprets a shorter distance, D will interpret the two ships meeting before C will. Remember, all we have in consistency here is velocity. We know the velocity. Everybody interprets the velocity as 0.6. In this case, C and D will both interpret A and B's ship of moving 0.6 towards C and D. They both agree on the velocity. But they disagree on distance. Again, this is the exact same phenomenon we have in the twin paradox, where you have two ships, two twins, they agree on the velocity of the objects, but they disagree on distance. So C sees a distance of 8, the gap distance of 8, but D sees a gap distance of 7.8. They interpret a different distance. So naturally, they interpret a different time. Okay, so assuming all these distances are light years, then it doesn't take much to figure out how long these events take place. So, from C's perspective, C sees a gap distance of 8 light years, and we divide that by 0.6 C. C will reach B, or C will think it has reached B at 13.33 years. However, from D's perspective, what does D see? Well, D sees a distance of 7.8 light years. We divide that by 0.6 C. D interprets a duration of 13 years for the journey between the gap is closed between C and B. So D will interpret the two ships meeting before C will, even though they're on the same. Okay, so a very simple question is that how is this even possible? If C and D are within the same frame of reference, how can they possibly interpret different distance? And how can they experience different time? Or experience different events? Well, first of all, they're not experiencing different time. They are under the same flow of time dilation, if they are under time dilation at all. The reason why is, as I said very early, length contraction is due to the center of an object. And if the object in question is moving, which in this case C and D, then the center point of that length contraction is to the observer, regardless based on where that observer is in question, not on the moving object itself. So again, suppose that C and D are not a single large ship. Suppose they're two different ships that are 1 light years apart, just moving in uniform motion with each other. They would get the exact same calculations. Again, this could be 3 ships. It could be 4 ships. They could be 5 ships. They could be, or you could have 100 different observers on this ship, all lined up on this ship, 1 light year ship. Or you can have 10 different ships, all kind of flying in line, and they would all come up with these different numbers. Because, again, their center point of their length contraction is different. So because C's length contraction is to itself. So length is contracting this way towards C. D's length contraction is also itself. So the length is contracting this way. Notice how because there are different points in absolute space and in relative space, they have experienced slightly different versions of length contraction. So they experience a different amount of distance. From D's perspective, the gap is 7.8, but in C's perspective, the gap is 8. They see 2 different distances because, again, because they're a part of each other, they have that distance, they have this different interpretation of length contraction. Their interpretation of distance is different from one another, even though they are technically seeing the same amount of length contraction. So again, they're seeing the same amount of length contraction, but their interpretation of the position of that length contraction is different. And when their position is different, then the time they experience would also be slightly different. Or, I mean, no, they experience the same time, but the events of when these events occur is different. So remember, as I said, I mean, you basically have, distance equals velocity times time. So we have velocity, that's constant. That's all we know, that's constant. But in this case, we have a difference in time, and we also have a difference in distance. The distance is different, or the interpretation of that distance is different. Now, one thing to note is that we're able to get these numbers because of the astronomical differences in distance between C and D. So if C and D were closer, then their length contraction differential will be so similar that it would be much harder to get these numbers. Presumably, let's say if it was a distance of 0.0001, then these numbers would be, the difference between the two will be a lot less because, again, they're so much closer to each other that this difference in interpretation will be, the number gap will be a lot smaller. So the further you are apart from one another, the bigger this number interpretation becomes. So in this case, they're 1 distance apart, or 1 light year apart, then they're able to get this massive gap between the two. Again, the bigger their gap, the bigger their distance. In fact, let's do another calculation. What happens if this distance is much, much bigger than 1? Okay, so as I said earlier, let's take a look at what happens when the distance between C and D is a lot longer. So we'll have this scenario here. Again, this is just the so-called true measurements. It's meant to just let you guys see what exactly is happening, so you guys aren't too confused. Okay, so we have a gap distance of 10, and C and D has a distance of 10. Okay, now, when C and D moves, we take a look at C's measurements. So C interprets that gap distance as length contracting down to 8. Pretty straightforward. 10 distance contracts 8 distance at a distance of 0.6 C. Not very hard to do. Now let's get D's measurements. Now D, on the other hand, and notice how the difference between the pictures are much more pronounced. Especially here. D, on the other hand, sees that distance. Remember here. The gap distance is 10 and the CD distance is 10. So the distance between B and D is 20. Remember that number. Now when we get down to D's measurements, D interprets that 20 distance as coming down to 16 distance. Again, length contraction. Then, from D's perspective, what is the gap distance? Well, it's not very difficult. If D sees a distance of 16 to B, and CD distance is 10, then the distance between B and C is obviously a 6. 16 subtracting 10 equals 6. So, this is 16, this is 2 distance here. Subtract the distance in C and D here, which is 10, which leads to the gap distance of 6. So, D interprets the gap distance of 6. C interprets a gap distance of 8. Okay, so that's not very hard to figure out. C interprets a gap distance of 8, which leads to 13.33 years, due to travel speed of 0.6. D, however, interprets a gap distance of 6, which takes only 10 years. Notice how, yes, they're on the same frame of reference, but they interpret different distances to each other. And because of that, they interpret different times of when these events occur. The events of the two ships meeting is not simultaneous to the two observers, C and D, even though they're on the same ship. Now, as I said, it's actually really easy to tell if you're on the moving object or stationary object. So, suppose you're in this dimension, you want to figure out if you're moving or stationary. Well, how do you do that? Well, it's very simple. All you need to do is have another observer on your ship at a different location of your ship. The longer your ship is, the easier it is to do this calculation. And you have them measure distance between itself and a point on your ship. So you pick one point on your ship. In our case, we pick point C, the leftmost point of our ship. We don't have to. We can also pick point D. We can also pick the middle point. It doesn't matter. The point is we pick one point and we have two observers on different parts of that ship make measurements to another object, which in the case is B. C and D will always measure different distances. Again, it doesn't have to be C and D. It could be three different objects. It could be three different observers, so there could be an observer in the middle of it. And again, the middle observer will also observe a difference between C and D. And again, it doesn't have to be a single ship. It could be two different ships and two different points in space. And they can both make this measurement. And again, they will measure different distances as we have calculated here. Alternatively, is we do the interception route, in which case when the two ships meet, and you time each other to see when the two ships intercept each other. In this case, the one that's further away, D, will see the C and B meet point before C will see itself meet B in time. I understand that's kind of confusing. How can D interpret C as meeting B before C does? Well, that's just a matter of simultaneity. But notice how D and C will interpret this event before B will see them meeting each other. Now, remember the ladder and barn paradox, where the stationary observer, the barn, sees the two events simultaneously. Yet, the moving observer, the ladder, sees two events happen at different times. Again, this is kind of the same thing. This is kind of going back to that. Where, again, if you're on the moving object, you will have inconsistent observations with somebody else on your same object. On the other hand, if you're on a stationary object, you will agree. Notice, C and D disagrees on the distance between B and C. They disagree on the gap distance, but A and B do agree on the gap distance. They have an agreement on the gap distance, and they will also agree on simultaneity. So when B sees to C, B sees it, A will see the exact same thing. C and D, they disagree. They see two different events happen at different times, and they also see two different distances. That is how you figure out who is moving and who's not. That is how you solve for absolute velocity. But remember, this calculation can only be made when objects are stretching fast enough. Obviously, if objects are moving much slower, let's say at walking speed or something, the length contraction would be so minute, it would be much, much harder to measure. But theoretically, as long as there's any amount of length contraction that's measurable, then we can use that to solve for absolute velocity. But this length contraction has to be measurable through what we can do. And again, this is not easy either, right? If we're talking about two ships moving at 0.6 times the speed of light, that's not actually easy to measure that velocity or measure that length contraction. But as long as we can take these snapshots, and as long as we can measure the distances and the gaps and the positioning of these objects, then yes, we can solve for absolute velocity. Now, one thing to note is that there's no actual symmetry between any of these observers. Although A and B technically do have symmetry, as they say the exact same thing, C and D don't even agree on the same events occurring. So, the implicit assumption of special relativity, when you can say that, you can always say that you're stationary, is that assumption that there is symmetry, but there is no actual symmetry. A and B, C and D disagree on the turns of events. They disagree on length contraction distance. They also disagree on when each event occurs. So there's no actual symmetry. And as I said earlier, the lack of symmetry is why you can determine who is moving and who is not. Okay, so the next thing is that I said earlier that, for example, we are calculating it based on the fact that we have sort of instantaneous, fast and light communication. The truth is, we don't actually need instantaneous or FTL communication. Because all we need to do is get everyone. So as soon as and again, in our second example, where there's just no station, the ships are never stationary. All you have is one ship approaching the other ship, moving towards the other ship. In fact, we don't need fast and light communication because all we need is very simple. Again, A and B are going to have the same clocks because again, they're not have time dilation with each other. Now C and D, their clocks would match each other, although their clocks would be dilated. But all we need to do is, again, when you have a ship approaching this way, or a ship approaching this way, we don't know yet which yet, you need to get all four people to write down when they saw this event occur, which is when C and B cross. To record, all you need to do is get all the four observers to record when that thing occurs, and then match the times. Because, again, when you get back together, you figure out that, there are two observers who match times, and two observers who don't have the same times. Then you can figure out who's moving and who's not, because the two who again, most likely, the two who have see the exact same time of this event occurring will have the same time, will be the stationary ship, while the two observers who saw a different time, in which case this event occur, will be on the moving ship. Again, even though their times would be different than theirs because of time dilation, but because their times can match each other, but they're different times, even though yes. Okay, so a very simple question would be, does this sort of break special relativity, or everything we know about physics? And I would say, not really, because special relativity is still relevant for things that are moving, not moving super fast. But again, as soon as things are moving to a point where it changes time and length, time dilation and length contraction, then yes, special relativity breaks down. Because it just doesn't work anymore. Because we can see here that once you move things fast enough, there is no longer symmetry between the two because they have different interpretations of length contraction. In fact, two different observers on the same ship, as long as they're reasonably far enough apart, they will have different interpretations of events due to the way length contractions work going all around them. So, and the next question is there a universal constant of acceleration? Is there a universal standard of velocity and what things are moving? Again, the same question that's in the twin paradox, and the answer is only if things are fast enough. If things are fast, if things are moving at speeds or generating length contraction and time dilation, then yes, there is an absolute universal sort of standard for velocity. As you can see here, we did a simple example, which is you have a universe with no stationary objects at all, with no planets or stars. We have that dimension. You have two objects moving towards each other in relativity, and we can figure out who's stationary. If we could do that, then yes, there is an absolute universal standard of velocity. Velocity is not absolutely relative. It is absolute, and it is absolutely is standard, and you can determine who is stationary and who's not, provided that these things are moving fast enough. Okay, and further research, and I will do more to kind of keep going, which is very simple. When we have two objects that are both moving, but one is moving faster than the other. And in this regard, we're going to do, and this will make things go even more complicated, and stay tuned for that, because that will be really, really cool, and I would love to kind of show you guys how that would work if we can determine, absolute velocity in that example.